Welcome to Chibuzor Math Physics. In today's video, we shall be looking at special relativity. Special relativity. By the end of this lesson, you should be able to state and discuss Einstein's two postulates regarding special relativity. Of course, Einstein's postulate is simply an assumption that help us understand those theories. You should be able to demonstrate your understanding of time dilation and apply it to physical problems. And you should also demonstrate and apply equation for relativistic length, momentum, mass, and that of energy. And by so doing, we look at how we derive those equations. There are two basic postulates by Einstein. The laws of physics are the same for all frames of reference, moving at a constant velocity with respect to each time. And the two postulate is that the free space velocity of light, here we refer to simply the speed of light. So the free space velocity of light is constant for all observers, and it is represented, and this is constant. It is 3 times 10 power 8 meter per second. So Einstein time equation, for the purpose of the derivation of this equation, you can refer to the previous video so that you know how we arrive at this equation. This is delta t, which means the relative time, or what the time measured in frame moving relative to actual event. Delta t naught is simply the proper time. Some people call it rest time, so you can as well say that this is the rest time when the object is at rest, or you say it is the proper time. So it is time measured in the same frame as the event itself. Relative velocity of two frames is represented by v, and free space velocity of light is c, and that's how we coined this formula. Change in t is equals to delta t naught divided by the root sign of 1 minus v squared, where delta t is the relative time, the delta t naught is the proper time or the rest time, v is the relative velocity of frames, and we have free space velocity. So now let's take the first example. Ship A passes ship B with relative velocity of 0.8 relative speed. This is 0.8 speed of light and 8% of velocity of light. So a woman aboard ship B, and that woman takes 4 seconds to walk the length of her ship. What time is recorded by the man in ship A? You can pause the video and try doing it yourself. Okay, so now let me show you what to do. First of all, you might need to write the given. What is given in this equation? We know that proper time is given by delta t naught, and delta t naught is simply 4 seconds. So this is 4 seconds. We are to find the relative time, and the relative time is delta t. So delta t is not given, but we have delta t naught, which is the proper time or the rest time. So applying the formula, we know our formula is delta t is equals to delta t naught divided by the square root of 1 minus v squared c squared. This will imply that delta t will be equal to, we know that we have delta t naught, which is the proper time, and this is 4 seconds. 4 seconds divided by the root sign of 1 minus 0.8. Here we have 0.8 as the relative velocity, so it is 0.8 squared. Remember, v is squared, so we have nothing to do with c squared because we are looking for delta t. So simply put c squared. Put this in the calculator, you will have 0.8 squared. 0.8 squared will give you 0.64. 0.64. So 4 divided by the root 1 minus 0.64. This will give us the delta t, which is the proper, we have the proper time, the relative time. Delta t will be equal to 6.67 seconds. 6.67 seconds, and this is the solution. Okay, now let us look at length contraction. Since we've talked about relatives, we've talked about in the previous video relative time and proper time. When there are two ships that move together, and we use our formula to find it using delta t, which is that of the relative time. We have delta t naught, which represents proper time. V simply is the relative velocity, and here we are given length contraction. So since time is affected by relative motion, length will also be different. So we have another question. For the purpose of derivation of this formula, refer also to the previous video where I derived all these formulas. So we are going to be applying this formula. L is equals to L naught into square root of 1 minus v squared, where L naught is proper length and L is the relative length. Of course, we know that V is the relative velocity. Of course, it is squared. So let's use this formula to calculate length contraction of an object. Here, a meter stick moves at 0.9 speed of light relative to an observer. What is the relative length as seen by the observer? You need to read the question very well and pay attention so that you are able to analyze. A meter stick moves at 0.9 speed of light relative to an observer. What is the relative length as seen by the observer? Using this formula, we know that since it is a meter, it means we simply have L. Remember in the previous video, L means proper length. So we simply have L. L will be, this proper length will be 1 meter. And you need to convert this. We know that 1 meter is equal to 100 centimeters. 1 meter is equal to 100 centimeters. So we are given 1 meter as the length, the proper length. So what will be, we are looking for is the relative length. And the relative length so we simply need to plug in what we have in the given equation. That will be 1 meter into 1 minus, we are given 0.9. 0.9 as the relative velocity. So it is 0.9 squared. 0.9 squared, c squared. So put this in your calculator, you will simply have this multiplied by this, but then since we need to change this to centimeter, so that we have 100 into 1 minus 0.9 squared will give us 0.81. 0.81. Therefore, our final answer recorded for the length by that observer would be 0.436. 0.436, which is 43.6 centimeter, because we have changed this to centimeter, so we are using 100. So this will be our solution. Now let's consider relativistic momentum. The basic conservation laws for momentum and energy cannot be violated due to this relativity. Of course, from our basic knowledge in thermodynamics, we know that energy can neither be destroyed nor created. It can only be transferred from one form to another. So we can't violate that law. Newton's equation for momentum, as we know it is mv, must be changed as follows to the account of relativity. For us to be able to calculate the relative momentum of any object, we have to consider this formula. P represents the momentum, so it is given by m naught v. M naught is the proper mass, often called the rest mass. Note that for large values of v, this equation can as well be reduced, and it will be reduced to m to be m naught divided by the root sign of 1 minus v squared, which is the relative velocity. So let's try to use this formula and apply in calculation and see how that can help us. The question says that the rest mass of an electron is 9.1 times 10 raised to power negative 31 kg. What is the relativistic mass if its velocity is 0.8 speed of light? So what we are given, we are to apply the formula. First of all, let's write our formula. It will be m is equals to m naught into the root. We know it is 1 minus v squared into c squared. So we simply plug in this into the formula. M will be 9.1 times 10 negative 31 kg divided by 1 minus 0.8. 0.6. This supposed to be 0.6, not 8. 0.6 squared, then c squared. This will give us 9.1 times 10 negative 31 into the root of 0.36. So our final solution would be 15.2 times 10 to the power of negative 31 kg. 31 kg. So this is the solution, and this is the mass, the one we are looking, the proper mass of this equation. In the next video, I shall be taking you through mass and energy. Prior to the theory of relativity,